All right, so we are switching the gears to security today, but I want to mention something about the project because I got a number of emails. So it turns out that from last year, Akka people made progress, and they actually have a logging facility now. And it's so there and so tempting to use, right? That would be wrong for me not to consider it. Okay, so here's the rule we make. Okay, you either write the logging from scratch and then provide the nice mechanism and whatnot, or you can use the Akka logging, but then I wanted to go a little bit further. I mean, put the effort that you save by using the Akka logging into a nicer logging facility so you can log state better integrated with the system, right? So I'm going to have two versions of the project. Use no Akka logging and then do what I said in the project. Use the Akka logging, but then you have to convince me that you went further. Not sure if that makes sense. Probably doesn't completely, but right? So the Akka logging already does the logging for you. It's still not complete. You still need to log into separate files. You need to find a way to log into separate files because, as I explained to you, you're serializing things, right? Serializing things is never good. So let's think about this. Right. Let's make this even a little bit more open-ended, like the second part of the project. Right? So I want you to rethink a little bit this logging facility to make it good for the second part of the project. And I want to see some reasonable effort for the logging. It's going to be graded separately from the second part. Another option is, if you want to be on the safe side, just do your own logging for the first part, but then switch and use the Akka's logging for the second part, and that's perfectly acceptable. For the second part of the project, you can use any tool you want. It doesn't have to be Scala. I want that to be understood. Okay? You're extremely good with certain libraries in JavaScript or Flash or whatever. Use that to show some nice visualization on top of the events. You want to switch to other esoteric languages that you know to do certain kinds of magic. For example, you could use Prolog to do some kind of an inference based on are certain properties of the messages true or not. Hey, use that. I just want you to show me skills you have applied to this specific problem, which is distributed debugging. Okay? Now, since it's debugging and not, per se, product building, it's very hard to actually sell a debugger. Okay? I mean, people don't pay for debuggers. Let me tell you that. Okay? So don't try to imagine, oh, I'm going to create this great company that's going to build a debugger, and then I'm going to sell the debugger and make lots of money. You won't. People don't buy debuggers. They use debuggers. They just don't buy debuggers. On the other hand, if you're part of a larger project and you run into trouble, which you inevitably will, basically you can use anything to rescue the project from the inside, right? So those people are going to put up with any tool that helps them find bugs. You see, when you have to argue what goes in the product, it's very hard to say, let's use this library or that library, because it's a very tricky decision to make. It's very tricky because it's long-term liability. How are we going to support that? Do we understand that? All that. But when it comes to, hey, I'll just find the mistakes we made in the program, I mean, people even use semi-magic to find mistakes. I mean, some people just can guess where the mistake is, right? And hey, that's good enough, as long as it rescues the project. So it's much easier to sell to your boss highly esoteric tools to find mistakes, but it's virtually impossible to sell things that will go in the main product. People that spent time in the industry probably already know this, right? So this is why I want you to really think big for this project. Use any skills you have to do something as different from the other people as possible. As long as you make me happy in those 15 minutes when you show your project, it's all nice, right? It's really open-ended. If you find any other thing that's interesting to do on top of this distributed debugging, I'm up for it. If it sounds too weird, pass it by me. But other than that, you can just go ahead and do it. Okay? For the first part, I do want to see your skill in designing a decent logger. Okay? So again, either go by the description and build the logging facility from scratch, or go with Akka logging, but then I want a very careful solution that takes it further than Akka. Don't just show me that you can use Akka. Okay, that's not going to be good enough. All right. Good. Hopefully, people are going to watch the movie to know that that's what I want, which you should. Okay, so let's talk about security, right? So, okay. Before we connected computers together, it used to be the case that performance was really the main concern, right? Nowadays, by far, security is the main, it's what should be the main concern. So let me put it like this. If your performance, it's a little bit worse than the other people, hey, maybe it's not, I mean, you lose some customers. With security, you can go from wealthy to extremely poor in the blink of an eye. Okay, so we've seen examples like this happening, and I just want to warn you. Everything you do in any product you will ever work forever, okay, because things are not going to get better, are just going to get worse, can bankrupt the company you're working for. And occasionally, the company that gets bankrupted will make the world know who's the person responsible for that. Okay, sometimes they won't, sometimes they will. If they do, your reputation is ruined forever. Okay? I want to give you some examples of just how bad things are. Some of the examples are as fresh as last week. Okay? So how many of you know about the big debacle with Adobe? So somehow Adobe managed not to mess up until last week. They were not in the news for many years. I mean, I don't remember. Well, they had some trouble with PDFs, right? People figure out very clever ways to exploit PDFs, which to a large extent is nonsensical. You think about the PDF as being this image format. It's as if somebody would exploit JPEGs. I mean, how can you exploit data? Well, it turns out PDFs are not quite data. They actually have programs embedded in them because of the PostScript, which might not be obvious at all, but in fact, it's a Turing-complete language. PostScript has a Turing-complete language. PDF, it's a compressed version of PostScript plus some other gizmos. It's actually possible to exploit it. But this is really not the big debacle. That was kind of, OK, Windows has problems, Linux has security exploits. It's kind of a fact of life. You deal with them. They are relatively confined, quite hard to exploit most of the time, and so on, right? But when it comes to access control, passwords, this is where the big mess-ups come into play. And they come into play because you cannot assume you're not going to lose the data, especially the encrypted version of the data. And just doing encryption is not good enough. Okay? So it used to be the case that if you encrypt, you're fine. And we're going to talk extensively about encryption. If you encrypt, you're fine. It turns out that the world has changed completely. It's not enough to encrypt. You can now break encryption, especially when you have weak passwords, so easily that in a couple of days, people are going to publish statistics about how bad the passwords on your websites are. So what I'm talking about is Adobe is in the news by first announcing that they lost encrypted, and they were encrypted. I'm going to explain to you why that's not enough in a few minutes. They lost encrypted passwords for something like 3 to 4 million people. Then they upgraded that to 38 million people, and then they said it's more like 140 million people. Which essentially means all the people that ever registered on their website, right? Because I don't think they have more than 140 million people that registered for their website. Within days, people started to publish statistics saying, what is the most, I mean, very interesting social studies can be done once you break encryption on a massive scale. By the way, Yahoo had encryption broken on a massive scale. It was now Adobe's turn, right? Things like the most popular password is, well, it turns out that on Adobe's website, one of the very popular passwords was Photoshop, which never showed up before. Adobe, minor variants of this. An all-time high popular password is 123456. And the next one is 12345678, which is stronger, yes, by about a microsecond, right? It's actually fascinating to see just how bad things are. I mean, so security, to a large extent, is something that both users and companies have to do. And you can do things about all of them, right? But the specific mess-up of Adobe is the encryption they used and how they kept the passwords on their side, okay? I will not only tell you what other people do, but I'll tell you about something that I'm thinking to actually incorporate into my own product, which I believe is a stronger encryption scheme. And I'm going to weave it into this story and point out to you what you could do, especially if the group of people that are going to use the system is not expected to be overly large. That's going to put some pressure on the system, but possibly it's going to solve other issues. Now, so there is something I want you to understand, right? It's not that we don't have good encryption methods. We have amazing encryption methods. It's that they are not used in the proper way, right? So it's as if you would have this extremely sophisticated lock on your door and you leave the windows open, pretty much. Okay, so a lot of the security exploits have nothing to do with a direct break of the encryption mechanism, except in Adobe's case, when they use something that used to be the standard about 15 years ago, and now it's simply inappropriate. Okay? So a particular danger, and I'm going to come back to this, a particular danger is not updating your security as time goes by. The fact that something was good 15 years ago doesn't make it good today. Okay? And to a large extent, I'm going to argue that transitioning from one system to another should have been almost a weekend job after, let's say, less than a month of development. Adobe should have switched from their encryption. So what I'm talking specifically is the fact that they broke all known security protocols with how you should deal with users' passwords, and have done something that actually is now a textbook example of how badly you can design a large system. They use something, first of all, old encryption, which is triple DES. And as I'm going to argue throughout these lectures, you shouldn't just simply encrypt the passwords of the users. You should do something that's called a one-way hash, okay, with tricks. Right? So you know what? Maybe that's a good warm-up. So let's just think about this very simple problem, okay, which is authentication. I'm going to go through requirements of the security system and so on, but one of the very basic ones is authentication. You pretend to be a certain user, and I need to make sure you are the certain user. Based on that and other gizmos I have in the system, I'm going to let you do or not do certain things. How do I know you are who you are? By the way, let me ask you, it turns out this is very subtle, so let me ask you even questions from real life. Right? How do you know that I am, for example, Alin Dobra? I come twice a week here, and how do you know I'm not some alien that just took my shape, right? I mean, we've seen so many movies in which aliens do a very good job at taking the shape of particular. How do I know I am who I am? Right? It turns out this is a very tricky question, especially when you don't have direct access to me, right? I mean, this is why disguise and other things work. Or, for example, I mean, physical appearance is very, I mean, I'm not going to say very easy, but doable to actually fake up. There are makeup artists that are pretty good at making people look like something else, right? So, tricky thing, very long-term problem. I mean, this existed for a very, very, very long time, right? And it's an essential problem. How do I make sure you are who you are? Now, it used to be that the standard is, oh, let's establish some sort of a secret between us, and we are the only ones knowing the secret, a password. And if you come up with the correct password, I know you are who you are. Now, it turns out that right now passwords have extremely bad reputations. They have extremely bad reputations because they are almost never used properly. Okay. So one classic one is 1, 2, 3, 4, 5, 6, right? Password. I mean, my daughter is 6, and we have a keypad on our condo, right? And she said, I want to know the code. And I said, look, you can pick any code you want, and I can program it, which is true. I can program it into the keypad. What code do you want? She was about to say 1, 2, 3, 4, and I said, you cannot say 1, 2, 3, 4. Oh my God, okay, now I have to think about something else. So I'm not going to tell you the number because I'm actually planning to put it in. But it's only semi-simple, right? But it's in human nature that you're going to do this. Or you put the password under the keyboard or things of this sort. By the way, most of the secretaries in the good old time, when the passwords came in, right, or people write their passwords somewhere on the board in front of their computer or things like that, okay? So this is very tricky because now we have the ability to check very large numbers of possible passwords, right? It's not only based on dictionaries. A brute force attack on 6 letters is almost trivial, okay? It can be done even on a cell phone now, right? And especially if you're just using simple encryption. So let's imagine that we have a very strong encryption method, okay? It doesn't even matter how strong it is. Well, it doesn't. If I have, right, a brute force attack, and this is crucial, by the way. The brute force attack is something that will remain as part of the cryptography forever. A brute force attack consists in enumerate all possible passwords from a space you think that fits the bill, and simply try all of those passwords and see if they go through, okay? Brute force attack, it's exactly what the name suggests, is brutal. I mean, it will eliminate, I mean, anything that's in a relatively small space. By the way, relatively small means trillions now. Anything that lives in a trillion space, it's breakable. we can break, using GPUs and special setups, we can break now, I think, for less than $1,000 in hardware, 1 billion keys per second. Right? So a space of 1 trillion, it's only 1,000 seconds. It's nothing. Right? So brute force attack, again, consists in just try all the passwords, know how you go to the encrypted version, and see if they match. Okay? The problem with decryption and, I'm sorry, with encryption and decryption, if the key is not particularly strong, right, you know that some of the passwords are going to be reasonably close to clear text. What you can do is simply try encryption keys, and probably this is what happened with Adobe, right? You can simply try encryption keys until the passwords look clearer, and when they do, you're basically done. Another particular problem with just encrypting passwords is you have to encrypt each password independently. If you encrypt very short text, you're more vulnerable than encrypting much longer text, right? All of these things pile up and results in this kind of issues in which we essentially have 140 million passwords breached. We are going to go through some of these techniques, and I will mention things that you can do better. Now, so one of the basic principles is this brute force attack. But there is another principle related to security, and somehow it's not on these slides. And people forget that this is one of the most important things. Is we have been trained to think that secret means don't tell me how you do it, and you do a certain trick, and nobody's going to guess the certain trick that you're doing. So there is another principle in the security community which turns out to be extremely important. Okay? And it's called no security via obscurity. Okay? So this is something that failed over and over and over again. I can give you some historical examples that people lost big wars because of that. Okay? Security through obscurity. So this is no. Okay, say no to security for obscurity. So what I mean by this is don't invent your own security mechanism thinking that because I'm going to keep secret the security mechanism, nobody's going to know about it, and it's going to be better than other security mechanisms because I kept it secret. It turns out that this is one of the worst things you can do. Okay? Now, it's completely counterintuitive because you might think if I keep it secret, if people don't even know what security I used, is better. It's as if you use a fancier lock that nobody has seen before. Well, it turns out that it doesn't work because it takes an enormous amount of effort to make a security system sturdy, an enormous amount of study. By cooking up your own, unless you put tremendous amount of effort into analyzing your own security system, it's probably far weaker than systems that are clearly known but have been analyzed much more. It turns out, and this is, again, counterintuitive, it turns out that you knowing how the security system works for a large class of security systems that have been designed doesn't help you at all in breaking the system. So a good security system is a system that has all the details in the public, has many implementations, and people have tried to break it all over the place, even knowing absolutely all the details, and it's still not possible to break it. Okay? So you can actually come up with very stringent standards for security. And it turns out that you can design systems that pass all those very stringent requirements. For example, one of the requirements is the following. And this, again, is not usually explained. How many people saw security in a networking class, for example? How many people took networking class? Right? So I'm sure you had some discussion there, but maybe I'm complementing some of that stuff. I have no idea what was discussed in the class. But usually the emphasis is on very technical things. I'm trying to stay more with the high-level issues. We'll do some technical stuff as well. Okay? So this is one of the basic requirements for symmetric encryption systems. I'm going to mention in a second what symmetric means. But symmetric is what you think security encryption is, and asymmetric is the weird one. So symmetric means if you have if you have the key, you can open it. If you don't have the key, you don't open it, because a symmetric key, it's easily derivable key. It's used to decrypt versus encrypt. So if you have the encryption key, it's easy to derive the decryption key because it's just a binary XOR. Okay? So the strength of a symmetric encryption system is judged, among other things, by how many pairs of clear text and encrypted text do you need in order to be able to derive the key. So here is something that would be devastatingly bad, because then a little bit of social engineering will get you the key. If it's possible, so think spy movies. Sophisticated key they have to get into whatever house, right? They go and they bump into people, they steal the key, and they just copy the key, or they do something like that, right? But imagine, for example, that I would say, you know what? OK, so for some reason you guessed what was the clear message pushed into the security system, and that's what's the encrypted message. If it would be relatively easy to derive the key, that's the problem. I mean, I don't care about the clear message, because I already had the clear message. But if it's relatively easy to derive the key from the pair clear encrypted message, all I have to do is do some social engineering to buy some such pairs, or to trick people into encrypting some stuff that I know what's in the clear text and derive the key. Now, simple encryption keys are completely vulnerable to this, right? So if, for example, if you use a fixed key all the time, even if it looks very complicated, right? If you just do a XOR between the key and the message, and you just look at what the encryption is, right? You completely derive the key. Done. So a good symmetric encryption algorithm, it's an encryption algorithm in which you need an enormous number of clear text, encrypted text, in order to derive the key. Just to give you an idea, for AES-256, it's believed that you need at least 2 to the 200 key pairs to derive the key, at least. The best known theoretical security attacks reduce the space from 2 to the 256 only a little bit below, and is definitely much larger than 2 to the 200. 2 to the 200 is such a large number, it's not worth talking about, right? So this is why you don't want to design your own encryption algorithm, because algorithms like AES-256 are known to have very good properties, okay? Again, no security for obscurity. So when it comes, by the way, you will make decisions about security. You have to. Even as a low-level developer, you have to make decisions, because sometimes they are not properly made by the people higher up, right? Security should actually be something that's done systemically for the entire ecosystem, properly thought out how the security protocol comes into play. It's almost never done in that way. We're already seeing the Adobe. I mean, think about it. If a company that makes a lot of money comes up with blunders as big as what Adobe did, that means it's basically just a Wild West out there when it comes to security. I mean, actually, that's only one example, by the way. Let me give you another one. PlayStation Network, right? By the way, so to give you an idea, we don't know how much money Adobe lost. And I'm going to mention in a second how you can lose money on this, right? We don't know yet what impact the security breach had on Adobe, but we know how big an impact the security breach on PlayStation Network had on Sony. It's estimated that they lost at least $100 million. And by the way, Sony is on the ropes as a company, is not doing well, and it could, in fact, within a decade, kind of be, go out of business, right? It's surprising, but that's how things look like. I mean, it's going down since the big PlayStation breach. The PlayStation breach was precisely about the fact that one developer did not do his job and wrote a dumb function, right? It's crucial when it comes to security to pick good random numbers. So one of the essential things that needs to be done as part of security is random numbers. I talked a little bit about random numbers before, right? If you use pseudo-random numbers and you can guess which is the next random number, you're extremely vulnerable. It doesn't matter what else you do, okay? Because most of the time, you're going to mix up randomness with other things, or derive certain keys in the security protocol from randomness. You don't have a good secure random number generator, you're in a really bad shape. The random number generator, for the purpose of security, in the code for PlayStation was something like this, right? And random return 5, okay? So the developer that was supposed to put there a secure random number generator wrote a function that returned 5, the most secure number. I mean, as some people argued, well, 5 is as random as any other number. Well, the trick with random numbers is it always has to be a different random number, right? And definitely not 5. So you can have the craziest encryption mechanisms, which, by the way, PlayStation did. I'm going to tell you some things about how they try to lock things down and so on. And we know so much about how to really lock things down and to make it very, very difficult to break. But then you do this. And once people found out this, it was on absolutely all the PlayStations. They just, poof, OK, now you can run anything on any of the PlayStations. And they breached PlayStation. This was not the only breach. This was a breach on the PlayStation itself. And then they stole all the passwords which were not properly encrypted on PlayStation Network, lost another 100 and something million passwords. The PR was so bad and the backslash was so bad. Again, they lost about $100 and $120 million just to deal with this thing. So how can you really lose money into this? I'm trying to instill in you as a developer a really big concern about security. How can you lose money out of this? Well, people start suing you, right? They say, hey, wait a second. I mean, especially if they properly pick the password and whatnot, they say, you were supposed to guard this for me, right? With PlayStation, it's really bad, and it could be bad for Adobe, because if they had encrypted credit card information, they, in fact, have to, I mean, there is a big class action lawsuit against you saying, hey, people started charging my credit card various things, you're to blame because they stole the credit card from you. How can you prove they didn't steal it from you, right? I mean, it can get really, really bad. And Visa basically sued them, and I mean, it can be very bad. OK, how can you do things right? I'm not going to say how you can do things right here. I mean, one of the essential things is, for example, use secure random number generator. By the way, there are libraries now. All you have to do is Google, find the right library, and convince your boss we cannot say int5. You have to use a proper library there. For example, in Java, there is a library that produces secure random numbers. Okay? All you need to do is Google secure random numbers. Look for a license that's not GPL. Done. Right? AES-256, it's extremely important to know about it, especially because it's hardware supported. I mentioned this earlier in the class. Now, one big problem with any encryption method is how efficient is it to encrypt and decrypt, right? Because that's what can make the system slow. If it takes a lot of effort to encrypt and decrypt, then you don't do it for performance reasons, right? You always sacrifice everything in the name of performance, right? There is no reason to do so anymore. This is supported in all the new, at least the servers, right? You need to put together a server. Don't even think about not using AES-256 almost all over the place, because the new AMD and Xeon, Intel Xeon processors can encrypt and decrypt at 2 gigabytes per second per core. Right. By the way, if you add up numbers in memory and you don't know what you're doing and you don't use the special SSE instructions, you're not going to achieve 2 gigabytes per second. You're only going to achieve 1. So it can go faster than almost anything else you can do in the system, okay? But it has to be streamlined and so on and so forth, right? So all you have to do is, in fact, use it. I believe the AES-256 implementations are going to pop up everywhere, which really means you shouldn't use security through obscurity, just use AES-256. Of course, you still have one job to do, and you have to do it right, which is pick the key, okay? All right, now, let me at least try to somewhat go through the slides. I don't want to stick only with the slides. They are too constraining. Okay. So let's talk a little bit more, in a slightly more structured way, right? Types of security threats to consider. And all of them are extremely important. And you have to be worried about all of them. And again, you have to be worried about what you write all the time if your program makes it somewhere on a server or it's used in a way that other people could exploit it, which means almost anything nowadays. Right? There are 4 specific things we have to be aware of, or blends of them, okay? Interception, interruption, modification, and fabrication. Okay, so let me go briefly through them and explain what they are, okay? Interception means you exchange a secret message in between 2 parties, and somehow I can read the secret message. This is what espionage is all about. Read the other party's secret messages, right? Good. Now, the modification is, let me not talk about interruption for a second. Modification is basically not only I can read the secret message, but I can change it. This is how wars can be started, right? You're sure that your communication channel is secure. Somebody figures out how to communicate based on your secure communication channel and puts words in your mouth, basically, right? Okay, we're going to talk extensively about especially how you resist something like modification, right? Well, modification is a weaker version of fabrication. Fabrication is you build it from scratch. But modification, there are subtle things you can do that you might get away with by just modifying things, but don't involve a full fabrication. For example, a particular vulnerability, and it doesn't require you to breach completely the security system, is to just do the same action twice. Okay? So imagine, for example, that you sell to somebody an airplane. I want to make the amount of money reasonable. Sell them an airplane, but you record the transaction, it's secure, and you say, hey, an easy way to make double the money is by just playing again the secure message to make the transaction go through twice. Of course, I'm not going to give you 2 airplanes, but I'm just going to charge you twice. Okay? So a particular subtle exploit you can have on the system is not so much invent new messages, but replay old messages. So a secure system has to be designed in such a way that you cannot replay old messages either. So by recording the messages that go through the unsecure channel, which, by the way, we have a gazillion ways to do right now, right, and replaying back the same message should not allow the same thing to go through again. Okay? So modification refers more to that. Fabrication is cook it up from scratch. Right? Now, of course, if you breach completely the secure system and you got the keys, you can do anything you want. And because it's digital, nobody can tell where the bits came from. Right? So it looks genuine. Okay? Now, something that used not to be among the security, but now it has to be there because it's even a bigger threat than all the other ones, is interruption. Okay? So it's not related to cryptography per se, but it's definitely security. So interruption is more about denial of service attacks. Okay? So what does that mean? It means somehow the system is kept busy by activities that have nothing to do with making progress and making money, right? Just doing something else and completely disrupting the things on which you make money, right? Well, these distributed denial of service attacks, I mean, they are used now to punish various organizations. Is the number one way to attract attention, okay? Well, it can be done for profit. For example, what you can do is you mount, so a denial of service attack really means I start attacking you, your systems are just dealing with the deluge of whatever request I'm making, your customers are not getting through, and then I send a ransom note to say, if you want me to stop the denial of service attack, pay this amount of money. And of course you can say, no, I'm not going to pay, but you might lose something like $10 million a day like Amazon was doing. So when Amazon was attacked, for example, or when eBay was attacked with the distributed denial of service attack in 2001, right? It was really bad. I mean, a disaster, right? eBay, for example, had to deal with millions of angry customers, right? So you had, for example, an auction that lasted 7 days. Well, it was mostly disrupted by the denial of service attack, so people ended up, instead of bidding and the price getting to a reasonable level, people ended up getting items for almost nothing because somehow they squeezed the request in between the things. And then, of course, they were very happy. But the unhappy people were the sellers who said, hey, you have to cancel this auction, you have to do something with it or whatever because it was unfair. The system wasn't even up most of the 7 days, right? Amazon, much worse, because people couldn't go and buy their books at the time and whatever, gadgets and things. And it's estimated that they are losing about $10 million a day, right? So how do you prevent something like this? Well, you don't make the life easy of these devices. So you see, because of capacity building, it's possible to deal with a lot of legitimate requests at the same time, and that's not so bad. The trouble comes when these denial of service attacks are asymmetric in the sense that with little effort you create a lot of work for the website. The classic example, and this was devastating, right? The classic example was the SYN attack on routers. And this is basically what happened in 2001. So if you would have sent only legitimate requests to the servers with load balancing and capacity building, they would have made things slower, but still things would have went through. But the specific attack on both eBay and Amazon was discovering an attack you can make on the router. Those are the worst, by the way. And this is why maybe a networking class is more appropriate for some of these things. But, right? So the architecture for most of these systems is you have a big router. This is the pipe to the internet. And then you do all kinds of other things. For example, load balancing, some front-end servers, some back-end servers, databases, and whatnot. Okay? So this router is key, and it's really just one device and possibly with a couple of redundancies. And usually these routers are capable of dealing with millions of simultaneous connections at the same time, and hundreds of millions to possibly now more of packets per second, right? Now, how that happens, that's Cisco magic. And this is why Cisco makes money, because they can do this kind of routers. But the trouble is, an attack on the router and disrupting the router takes down the entire site, right? It doesn't matter that your servers here are very happy and ready for customer requests. They're never going to get the request because the router was attacked. So that's basically what happened. A vulnerability was discovered in the router. And these guys, all they had to do is disrupt the router. It is not even a big denial of service attack with many machines. You just make the router. I mean, literally what they were doing, that specifically was a SYN attack. Because the router had to allocate resources for every connection open in order to keep track of how much information moves through, right? To do some flow analysis. The specific attack was open connections and never send anything on connections. Just open enough connections to make the router run out of memory, and then the router reboots, right? So that this is how the whole thing went, right? The router was coming up. Within a few seconds, again, the SYN attack filled the buffers. The router resets. If it's staying up a couple of seconds, going down, up and down, and up and down. I'll go and do something on the website, right? They fixed the vulnerability. So you can have things like configuration vulnerabilities, right? They are configured in such a way, if you know that everybody does the same mistake in the configuration, you can create havoc by simply getting packets to go circulate between the routers. They are supposed to go on a tree, take a networking class, and see, right? These kind of SYN attacks, you make them run out of memory, right? Or you can do just an honest-to-God denial of service attack in which you just put a lot of connections in the hope that you're going to overwhelm the backend stuff. Now, overwhelming the backend stuff usually doesn't work with something like Amazon or eBay because of the capacity building, right? I wouldn't be surprised if Amazon got in the business of cloud computing mostly to deal with this massive kind of problems, right? So they overbuild capacity by at least a factor of 10 just to deal with these denial of service attacks because of the lessons in 2001. But for example, government agencies are not particularly good at this, right? So then one favorite way to punish government agencies, for example, this is what Anonymous does, is they just make sure that somehow they get 1 million computers to just send requests to that website. And then the traffic goes from some normal tricklish traffic that, okay, your engineers dealt with skyrocket, and then everything fails. How many of you heard about the /dot effect? How many of you know what /dot is? Right now it's irrelevant, but it used to be great, right? So /dot was the first website for news for nerds, right? It used to be extremely popular before Dig and way before Reddit, and now almost nobody goes there because it's whatever, okay? But the /dot effect is an unplanned denial of service attack on normal websites. So what I mean by that is, so this is basically what could have happened. You host, for example, on your website some interesting thing. Somebody on /dot notices it and posts it on /dot. They have no intention to kill your website. They post it, but you have millions of people saying, wow, that's interesting, and clicking on it. So you go from a couple of hundred requests per day to millions of requests per day. That's a sure thing to take down almost any website, right? So websites that survived the /dot effect was a matter of pride, right? It's like, hey, we somehow survived this big deluge of requests, which were in fact legitimate requests. And it's very hard. So by the way, this is more related to capacity planning. So sometimes you spill over from security into capacity planning. It's how do you deal with these extremely large spikes? Within /dot effect, I mean, it's considered to be a genuine /dot effect if the traffic goes up by at least a factor of 100. Right? Otherwise, it's not interesting. Okay? But sometimes it's done on purpose. So especially interruption is very, very tricky. Right? Now, there is something extremely important about security which I want you to understand. The bad guys never play by the rules. Never. Okay? You don't really need to break the encryption system. Actually, almost nobody ever breaks the encryption system. All you need to do is find mistakes in how the encryption was actually used to exploit it. So let me give you a bunch of examples to get an idea how nasty things can actually get, okay, from this point of view, and just how big of a task you actually have to protect the system. There's no, by the way, there's no such thing as fully protecting a system. There is only making it expensive to attack, right? So what you want is not to protect the system because you can't. What you want is to make it exorbitant to successfully attack the system, okay? So a bunch of very, very interesting examples, and I need to mention this anyway. How many of you know about quantum cryptography? Well, it's more, right, so, okay. So here's the bottom line, right? All the encryption methods we have are based on the fact that we keep some sort of a key secret. And by using, if you don't have access to that key, it's going to be computationally hard to figure out what's happening in there. But it turns out that physicists figured out that you can have physical processes for which you can tell if they have been tampered with. Right? And not only if they have been tampered with, you can actually make sure at the physical level that they cannot be tampered with. And this is why quantum cryptography is all about. Okay? So it's a very funky kind of process, but basically what you do, in principle, is you produce a pair of particles. These two particles are linked together through, by the way, this is real magic because nobody fully understands how this works, right? It's called quantum entanglement. So you have two particles that are entangled. You push these two particles apart, and you essentially keep one, and you send the other one to the destination, okay? Now, you haven't sent any message in this way. Once the other party gets a hold of the particle, anything you do to this particle happens to the other particle, okay? So in this way, if you push this guy up, the other guy goes up. If you push this down, the other guy goes down, and you can send messages through this. It's not enough to have only one particle. You have an ensemble of particles and all this kind of stuff, okay? So why is it bad? Because you see, you cannot trap the particle and not destroy the entanglement unless you're on the other side. You simply cannot intercept this at the physical level. I'm not going to go into all the details. Okay? Good. So that sounds great, and people are working on these things. The problem is, by the way, the fact that you need a continuous optic fiber. You do this with lasers. You produce entangled photons. You need a continuous fiber because you cannot amplify the signal in any way. If you capture the particle and you try to retransmit it, you broke the entanglement. So it really has to be an uninterrupted photon that goes on the other side. Okay? Okay, well, that's some obstacle, but people managed to lay fiber that goes for something like 100 miles, okay, without amplification. Okay, so you could have two secure sites and do quantum entanglement. But here is an interesting attack on it that nobody expected. So two companies had commercial products for quantum cryptography that said, look, we can prove you cannot break this. You can't break it. Okay, so get used to the idea. Well, that wasn't good enough for a bunch of researchers that actually found a way to trick it. Okay? And the way to trick it is very surprising. So what they did is the following. Instead of trying to break the entanglement, which you can't because it's a physical process, they said, what we are going to do is fool the transmitter and the receiver. So they cut the fiber. Okay? To fool the transmitter, they were sending a very powerful laser signal through the fiber back, blinding completely the sensor of the transmitter. The transmitter got completely confused and then communicating with the other side as if, I mean, they captured the entangled particle and blinding the other guy in the back. So what I'm trying to say is you can do all kinds of tricks that have nothing to do with the cryptographic method itself that are side channels and still trick the system and still go through. Okay? Let me give you another example which I heard in a talk at Cornell. This was about 12 years ago, and is more related to asymmetric keys, which we still need to talk about. Okay? And it was surprising to me just how many tricks you can do to break the system. By the way, this particular vulnerability is closed, but variants of it that are more tricky to exploit but still exploitable are still open. So RSA, which we still have to talk about, it's both an algorithm and a company, a very successful company, right? It's building this public key encryption software, and the trick there is never to be able to find the private decryption key. So you have a public, private. A public-private pair, I still need to talk about them to explain how the magic works, okay? But essentially the idea is if you have the public key, you cannot derive the private key from it, right? And you cannot decrypt messages without the private key. So I can take your public key, encrypt a message, and only whoever has the private key can decrypt it. This is why it's called asymmetric key, because you cannot derive one key from the other key. Well, it turns out that you can easily derive the public key from the private key, but you cannot derive the private key from the public key. At least we don't know how. And by the way, e-commerce is based on this because it's exactly what the SSL certificates are, right? So SSL certificates are essentially the public version of the private key, right? And you have a certificate authority like VeriSign that says, yes, this particular company is the only one that has the private key for this. Okay, we're going to get back to that in later today or maybe Thursday. Okay. Now, the trick here is not to be able to find the private key. But at some point, somebody has to use the private key to decrypt the message. Okay. So they had physical devices, for example, these tags that you sometimes see with a special counter, right? And those physical devices had the key built into them. So the RSA went to great lengths to make sure that you cannot extract that private key, right? Including things like if you try to open the device, it has an explosive charge or things like this, and it self-destroys. Not a big one. It's not going to destroy anything except the device itself. For example, IBM, it's still selling this secure hard drives that are tamper-proof. Try to open them, they literally explode. Okay? Not to be able to get to the insides, because then electron microscopes and other things could be helpful to get this. But people found a very ingenious way to attack a system like this. Okay? This is going to sound very surprising, I hope. Okay? And this has to do with how the software was written. So normally when you think software, you say, hey, what kind of mistakes can I actually have to breach the security? Well, this one specifically is about measuring the power consumption. Okay, so this is a trick people use to, in fact, within a few seconds to derive the private key. Okay, they used a decent $100 essentially measuring tool, right, to measure the power consumption, and they figured out that because of how the code was written, the system was using a little bit more power when processing a 1 versus a 0 in the private key. That's usually the case, because when you process a 1, you have to do some computation. When you have a 0, it multiplies by 0, and you don't have to do the computation. So in a natural way, if you write the software, the zeros and ones are asymmetric. This is a completely crazy kind of symmetry, right? So because of that, essentially all they had to do, right, with something like an oscilloscope, is to look at the power consumption, and they literally saw very clearly a 1, 0, 0, 1, 0, 0, 1, 0, 0, good, private key, done. This was supposed not to be breakable even if you had a computer of the size of the universe and run for a gazillion years, and was breakable within a few seconds by putting the right oscilloscope on the system, right? So what I'm trying to say is security is very tricky because it can be attacked in many, many, many different ways that are very surprising, and new ways come into place all the time. There is a particularly crazy set of researchers at Princeton that are responsible for this weird attacks, okay? Weird kind of attacks that have nothing to do with breaking the encryption, okay? So how do you fix this? Well, you start writing the code in a perfectly symmetric way, so the keys are symmetric. Well, it turns out it's still vulnerable for something called a differential attack, in which groups of zeros and ones still have a slightly different profile in the power. And you see, when it comes to deriving private keys, any advantage can be exploited, right? So even any of these cryptographic systems, if it goes a little bit left or a little bit right statistically, you can exploit that. Any statistical deviation from a perfectly balanced system can actually be exploited, and there is a vast amount of literature how you can actually do that, right? Other things, for example, are related to secure languages, for example, like Java. Right? So one of the big claims to fame of Java is the fact that it's in fact a secure language. It's based on essentially type theory, and when an object has a certain type, you cannot transform it into another type. This has to do more with rights escalation. You have partial rights to execute on a system, but not, let's say, root access, and you escalate the normal rights to root access, right? So these guys from Princeton showed a very interesting kind of attack, right, on a system like this. And the attack essentially consisted in writing a special Java program, and then somehow either waiting or hitting the machine and let the machine start making mistakes. So what they did is they wrote a program that they could exploit a single random bit flip in memory, right? So if a bit flips by any means, it doesn't matter. If a bit flips in memory, you can escalate the writes and claim to, I mean, it takes a little bit of doing, and you have to know what you're doing. It's not something completely trivial by any stretch of imagination, right? But they showed that by any mechanism that flips a bit, if you have a specific layout in memory, you can actually exploit it and escalate the writes. And then they described a bunch of methods which they tested themselves to make the bits flip. One of them is, for example, to just raise the temperature in the room, right? So the server is in a special room. You just take one of those $100 heaters and just hit it underneath to overwhelm the air conditioning unit, right? What happens is when you hit the room, because of thermodynamic effects, the memory at a certain temperature starts to flip more and more, probabilistic, more and more bits. What you want is to have bit flips, but not too many of them, because then the operating system crashes. And they literally had a demo in which they had a machine, they were hitting it, and they exploited it, and they escalated to root access, right? So the point here is I don't want you to remember all these things, because these things change all the time. Is when it comes to security, very weird stuff can go on to exploit your system. But most of the time, it's about simple mistakes people make, right? Things like random function that returns 5, or not using state-of-the-art known methods, at least for today, to work well like Adobe did, okay? All right, let's move on. I'm going to come back to these things because I need to talk about them. Okay, now I don't want to talk, okay. So when it comes to security, again, you have multiple communities, both in research and then you have what happens in practice. One of the best, most trustworthy communities, and I want you to understand that you can trust somebody here, is the cryptography community. Cryptography, it's more a mathematical kind of issue. And it's all about how can we design cryptographic methods. They don't say how you should use them, but how can you design cryptographic methods that can resist all kinds of attacks. So if I would trust anything, it would be things like AES-256 or asymmetric key algorithms like RSA or elliptic curves, right? Now, I wouldn't necessarily trust libraries and other specific implementation, but the algorithms themselves, right? So let's at least get that out of the way. The cryptographic community does fantastic work at coming up with such cryptographic protocols, algorithms, and analyzing them, okay? Then there is kind of the deployment part, is how do you combine cryptographic primitives and other mechanisms in order to actually build a secure system? You see, cryptography per se doesn't do anything to you, right? You have to use it, and most of the time, mistakes in using it can be exploited much, much, much easier than breaking the encryption. For example, let me give you another surprising thing, and apparently 98% of the web is vulnerable to this, okay? So we have SSL, which the algorithm itself is known for many years. It uses RSA. It's known for many years. Nobody knows how to really exploit it. It takes a tremendous amount of CPU to break anything. They managed to break RSA 128, and I think at the time they used some tens of thousands of computers, right? On the web, you have now AES 1024, and some people use 2048, the size of the key. 2048 is considered military level encryption, right? But it turns out that when it comes to this pair, public-private key, the size of the key matters, okay? Because the longer the key, these algorithms are believed to be exponential. Now, why believed? I mean, it's related to this core problem, P versus NP. Actually, it's weird, but RSA is not even known to be NP complete. It's not even believed to be NP complete. It's somewhere in between, but it's still very hard. Okay, so even if you say P is equal to NP, it won't tell you if you can break RSA, you cannot break RSA. But no algorithm that's not exponential is known for something like RSA. Now, elliptic curve is known to be NP. Okay, so look at this and say, hey, I have big keys and I do this stuff. But these keys are special things. We need to talk about them. Essentially, for RSA, the private key consists in 2 large prime numbers. Now, that's not something that the user would type. Okay, so when users type passwords, users do all kinds of weird things like 1, 2, 3, 4, 5, 6, okay? Because the system says it must be at least 6 digits wide, right? But any mess up in here with respect to how you pick the key, it's built into the implementation. So the specific vulnerability, which apparently affects 98% of the computers when they use OpenSSL out there, is the fact that they don't use a good enough random number generator when they pick the private key. So to pick the private key, you have to pick these 2 large prime numbers. And if you don't have a good cryptographically secure random number generator to walk into a large space and you walk into a smaller space, if you have any defects in the random number generator, they can actually be exploited. If you pick random numbers from a relatively small space, it doesn't matter how big the key space looks like. If you're not picking uniformly from that space or close to uniformly, it can be exploited, and you can actually guess what the private key is, in which case it's a complete disaster, right? So I don't know if you know, but it starts to be really bad now because of the NSA. I don't want to talk any politics about this, but NSA managed to break a lot of these keys by various means, sometimes buying the private key and whatnot. And VeriSign, which is an international organization, right, has as its base policy, if we find proof that somebody has access to your private key, we invalidate your SSL certificate. And they started invalidating SSL certificates of various companies because it was in the news that NSA actually has their private key, which is a complete disaster, right? Oracle is in shambles, and Yahoo is in shambles, and so on, because apparently they were forced to make the private key available to NSA, and now the international organizations and other countries say this is unacceptable. Basically, NSA can read everything on the web, and that's really bad, okay, especially by other countries, right? But it's not always just some sort of a very clever way to break it. I mean, sometimes they just ask in the right way to get it. I mean, any way to get a key, it's a good way to get a key, right? So, all right, good. So, Globus is basically a distributed system that tries to combine some sort of security mechanisms with this idea that you need lots of users from multiple organizations to somehow access resources. I don't want to go into all the details, but this is one of the core issues you would have to solve in almost anything you're going to be involved, is how do you use properly security primitives to build something much, much larger than that, right? Because it's not only about sending little messages from here to there that are actually secure, but about very complex ecosystems in which you have to assure that the person is who they are supposed to be, have access to what they are supposed to have and whatnot, right? For example, think even about the file system on your computers, right? Somehow you have to make sure that the specific user on a server has access to this specific file. Of course, the first one is this user who they claim they are? And that's the biggest issue, right? Authentication. I was supposed to have another slide here. OK. Yeah, I managed not to put it. So another core issue, there are basically 4 critical mechanisms that can be used in a system to deal with security. And let me put them down. Somehow they didn't make it to the slides, right? So the first mechanism that's useful is obviously encryption. So that means you somehow take clear text and make it garbled, and unless you have some magic key, you cannot see it. Encryption by itself is not particularly useful. The other one is authentication. So how many of you know about this famous hacker now, Robert Minch, I think it was his name? He eventually went to prison. He managed to break into the phone system of pretty much everybody, do whatever he wanted. Broke most of the security systems on the planet and had a lot of fun doing so. This guy never bothered to break any encryption mechanism. He was just using social engineering, calling them and pretending that's one of the sysadmins that forgot the password, and the people just giving him passwords over the phone, right? He was just very good at talking to people and getting whatever he wanted from people, right? So social engineering, it's a much, much better way to breach security. How many of you follow at least some of the details about Snowden and how he managed to just get access to all of those documents? I mean, in principle, he was a relatively lowly employee, a contractor that was not even part of the core NSA. But nevertheless, he managed to get access to documents that only specific generals were entitled to. Okay? He used a lot of social engineering as well. First of all, he escalated rights because he was an admin, but also, again, borrowing people's credentials because he forgot his, hey, I forgot my key, can I borrow your key? That, well, in a secure system, because of other issues we're going to talk about, essentially that means I can blame on you the access, right? If the key identifies you, not only allows me access to the system, oops, and it's easy in a cryptographic system to make sure that happens, okay? We're going to talk about that. So authentication is crucial. Social engineering can help potentially with escalating some of the rights there. Authorization. So authentication is related to prove to me you are who you are, but authorization has more to do with escalating rights from low-level rights to high-level rights, right? They know who I am, and I'm supposed to have access only to these low-level files, but somehow I trick the system and I have access to things beyond that, right? If you have no access to the system at all, then it starts to be problematic. But a potential big problem is you have some rights and you escalate them to full rights. Okay? For example, Snowden did as much damage as he did, mostly because he had access to some things, and through social engineering and other tricks, he had escalated to a really, really high level. Okay? Now, something that usually you might not think about this, but in fact turns out to be a pretty good deterrent, unless you run away in a foreign country, is auditing. Okay, so what auditing is, and it's crucial, I mean, especially when you have to design systems, you almost never think about auditing, but auditing turns out to be one of the best deterrents, especially if done right. Okay, so auditing has to do with making sure that there is a track record of who accessed what, and it cannot be deleted or faked. Okay, there are various ways to try to get close to that, and to build something that normally would be very hard to fake up, right? So for example, imagine that, for example, what happened with Snowden. There are all these secret documents, and you have rights to look at some of them. But if you do look, then there is some sort of information written in a database or in a log, and the logs can then be analyzed at the end of the day or the end of the week, and people can figure out that you access that. For example, my wife works at Shands, and obviously she can look at patient records because she's supposed to keep them alive, and if you don't look at their records, you can't know what disease they have. But it's all audited, and every now and then they will make sure you only look at the patients you in fact had in your care and not other patients, and essentially you get fired if you looked at some other patients. So they're not preventing you from looking at things, because it is very hard to have a system in which you really taught the system who has what rights to look, especially when it comes to saving people's lives, right? You want to make sure people have fast access to the system, and you don't want to have 5 bosses telling you who has access to what and making a mistake in locking people out of the system. So it's better to allow people access to everything, but you just make sure that if you look at the record, somebody notices and they can go back and do something about it. This is what auditing is all about. It turns out that if you have good auditing, most people won't do bad things, especially if the audit is in fact enforced regularly, right? And if at the end of the week, once you look at something you're not supposed to look, at the end of the week your boss comes, hey, why did you look at the record of that person? You do it once more and you're fired, I guarantee you won't look at that anymore. It's rumored, for example, that Google has a very good auditing system internally. I mean, I never worked at Google and so on, but it's one way to get fired out of Google extremely fast is to access data you're not supposed to access, right? And that's mainly done through auditing. Okay? That can be as easy as if you use a certain key, a log is written and the log is permanently written on a particular device. You can even go to extremes in which you use write once memory, in which when you write it, you can basically make sure it cannot be written again, right? There is memory like this in which a physical process basically burns the bits in. It used to be very popular. The ROM memory is probably much older than any of you might be aware of it. I'm sorry?
CD-ROM is write only.
Well, I'm sorry. CD-ROM is write only. So, for example, even basic things like this, you say, hey, at the end of the day, we burn a CD-ROM and we put it in a vault. And at the end of the week or the end of the month, we go through those CD-ROMs with armed people, and we see who looked at what you're not supposed to look. I guarantee you a lot less people would be doing nasty things. Okay? So don't dismiss this and build lots of auditing mechanisms in your software.
Is encryption part of authentication? Because when you enter your identity, you would encrypt it before sending it for verification.
Okay, so we want to keep this issue separate. Encryption is a very good tool to have, but is not necessarily sufficient by itself. When it comes to authentication, you see, it's a matter of start with a good seed of some truth, and then the rest of it can be encryption, right? But the trick is, how do I know you are who you are in the first place? You see, once I give you a key, maybe the key is proper, and we can use encryption from now on to make it easy. So encryption can be used to make your life easy once you establish authentication, at least the initial version of authentication, but you cannot really authenticate people by encryption alone, right? So again, ask yourself the question, how do I really know you are who you are? For example, even about students in this class, right? How do I know you're the student with that specific name? Oh, you say, yeah, but I have an ID. But then, again, you could have tricked the people that gave you the ID, right? This is what fake IDs are all about, right? And for example, how does UF know you are who you are? They ask for an ID, right? Okay, how do the state people know you are who you are? Right? It goes down to something like, ultimately the trust is established more through an auditing trail than anything else, right? So they essentially say is, yes, you are who you are because you have a long enough history that we can actually check to make sure you are who you are, but it's still not a particularly good definition of you are who you are, right? So what I'm trying to say is some of these issues are fundamental, right? And we're going to see when we talk about encryption, symmetric encryption, this is why you need third parties that vouch that you are who you are, right?
In that case, authentication becomes a bottleneck if you break the authentication.
No, but again, this is where the encryption comes into play. So a particularly good way to do authentication is to have a really high standard until you establish a secret key and then base the rest of the authentication on the secret key. This is, for example, why I believe authentication based on public-private key, it's better than authentication based on a key you type all the time. So what's a problem with a key that you type all the time? First of all, you type it all the time, right? So that means it's more vulnerable to eavesdropping. The second one is, for example, how would the server check that the key is correct? Well, the server presumably will get the key and then check somehow that the key is correct. But the server getting the key, it's already a vulnerability. I want you to understand that because, first of all, for example, if somebody breached the connection, secure or not secure, between me and the server, they can eavesdrop. And it doesn't matter how long your password is. If somebody can listen to it and record it, then it can be a megabyte long. It's still easily recordable, right?
Well, also there's password reuse, right? You use the same password on two different secure sites, but let's say one of them is hacked, then the other secure site, even as secure as it can be with the password you have to.
Right, so that's another issue. So there was an XKCD, by the way, this is a comic that you should all read. XKCD comic about how to really do massive damage. They said, set up a mildly useful website, ask people to sign up and put a password. People reuse the password and use their password to go on all the other websites and log in into the system, right? So it's definitely a big issue. Now, what I will be, maybe we should go through this exercise once I explain a little bit about how the asymmetric keys work. So, for example, how many of you, when trying to log in into servers and whatnot, are using, for example, the private public key pairs rather than typing passwords to go into the server without a password? Well, no, I would strongly argue you all should. And I would strongly argue you all should because it's, in fact, much more secure as long as you make sure that your machine is secure. Okay? So, for example, the problem that Adobe had is, again, that the users were pushing the passwords, the credentials of the passwords to the website, and they somehow, how do you verify that you have the correct password? This is one of the fundamental questions, right? You type a password. How do I make sure it's the correct password? I need something to compare against, right? That's the main issue. Now, some companies don't even bother to encrypt, and they just keep the password as a nice field in the database, right? Great. Like Sony. They were planning to encrypt. This is what they told the world. It was on in the plan. We just never got to do it, right, the Sony actually had a clear password. So clear passwords are by far the best, okay? But definitely will get the job done, right? So literally, that means I have a table, and I have the user and password. In your web app, the user types the password. The password, let's say, goes through a secure channel, SSL or whatnot. It doesn't even matter. The password goes to the server. The server says, pull the record from the database and just do a compare. Very simple, nice, done. Trouble is, you get a hold of this table, and eventually people will, if there is a big incentive to do so, you have the passwords for everybody, right? Because clearly it's a big, big, big issue. But then the question is, how can you compare, how can you make sure a password is correct without having the password in the clear? Well, you could do another thing, which is what Adobe did. You encrypt the field. But that means you have a secret key that lives on the server. And then, when the user types the password comes in the clear on the server. You use your secret key, decrypt, bring the encrypted record from the disk, decrypt in memory, and then do the compare. That's another way to do it. It turns out that this is not particularly good either. I mean, with AES-256, it would possibly be better. It has a particular vulnerability, though. The fact that the server must have somewhere the encryption key, okay? Now, it turns out, right, so think about this even in terms of physical devices. You say, oh, think about how can you keep the key secure? This is a big issue in security as well, right? It's not only that you have sophisticated keys, but you keep the key itself secure. How do you know the key is secure? Think even about the physical key, right? Again, spy movies. Most of the time, they bump into it and steal your keys. They copy the key. They put the key back into your pocket. It takes some skill, but it's doable, okay? You didn't protect the key particularly well. Think about now some kind of an electronic key. Where do you keep that key? You see, if a human has to type the key, at least the key is in the head of the human, makes it a little bit harder to extract, okay? Maybe, right? But on a system, automatic system like what Adobe had, the key is somewhere. By the way, this, in fact, was exploited, and the fact that people essentially managed not to hide that key well enough. So you can think about, OK, I'm going to have this clever way to hide the key. Because ultimately, anything could be a key. And you can say, I'm going to write a program that extracts bits from all over the place in memory and form the key or whatnot. But you see, you wrote a program, and I can go steal the program and disassemble the program. You can obscure that program over and over and over again. If there is a big incentive for me, I will go and either disassemble everything and understand everything and figure out where you're hiding that key. Or I can just wait for a mistake. Classic example is breaking the security of the DVDs. How many people know the story with DVD John? So the story was like this, and it's exactly this kind of a situation, okay? In which, when they established the security, so what I'm trying to say here is, virtually all major security systems, especially when protecting media, were breached, which means security is a very serious business, and you cannot just do a little bit of something there and be fine. If there is a big incentive for people to breach it, they will find a way to breach it, so you have to be extremely concerned about this. So when it came to the DVDs, they wanted to make sure that the DVDs play only in specific devices. Why? Because they wanted to make money out of licensing the devices. You see, if the media can be played by any device, you cannot control who plays it and who doesn't play it. You lost control, right? They were talking about piracy and whatnot, but it was more about control than piracy. And it was more about, I mean, lots of people claim about recouping the development money through licensing than anything else. So they came up with a security mechanism so that you, in fact, needed to have a key to be able to decrypt the DVD in order to play it on a specific device. Now, they've done that, and the scheme looks good, except that they completely messed up something crucial, and then it was down the drain. Okay, so all you need is a little bit of lag in, and then you can exploit other things, and then it escalates, and then it's really bad. So part of the disk, right, part of the information, I mean, all the information on the disk was encrypted, except that part of the disk, let me draw a box because it's a little bit easier to understand. So most of it is just the encrypted movie. If you don't have a specific key, you cannot read the movie. So in order to encrypt the movie, they had some kind of a media key. So the media key was a random key that was used to encrypt this entire DVD. You don't have that key, you cannot read it. But of course, the question is, how do you know the media key? In order to let devices know the media key, right, what they did is they took the media key and encrypted the media key with device keys. They combined the device key plus media keys to produce encrypted versions of the media key and stored them on the disk. Right? So they did not store the media key that was generated. They just stored the device key plus media key stored on the disk. Then, for every manufacturer, they allocated one of these device keys. So if you really wanted to build a DVD player, you in fact had to pay whoever developed the DVDs. Well, Sony, I'm sure, was involved, right? You have to pay a large licensing cost to Sony. They gave you one of the hundreds of slots that they had in there, right? And then you hardwired the encryption key into your device. So your device, essentially, when it started, it knew that it has to go to location 175, pull from the table location 175, decrypt it with the only key you had access to, which was the device key, find the media key, you can read the whole DVD. Okay? Now, if you do this in hardware, it's harder to exploit because you need electron microscopes and some really fancy stuff. Okay? Of course, people were mad because they wanted to play DVDs on their normal systems, and then the hacker, not even the hacker community, it's kind of the hobbyist community said, hey, let's look a little bit at this DVD stuff. Okay. So they knew that the best way to attack the system is to attack software players. Why? Because software players must have the decryption key in memory at some point in order to find the media key. You see, finding the media key was not a particularly interesting exercise because there were other ways to steal the content of the DVD. So this did not prevent people from stealing the content of the DVD because you still have to play it on a screen. All they had to do is to make sure they can do very good screen capture. They I mean, the DVD, software DVD player was playing it, screen capture was capturing it, you still had good quality movies out there. It wasn't even that big of an exercise to find the media key because the software player had to keep it relatively in the clear to be able to decrypt the media. And they published essentially media keys for a lot of the DVDs, but it took quite a lot of effort to find the media key. The big prize was to find one of the device keys, because if you find the device key, you can build it into, let's say, an open source media player, and then you can play any DVD. Okay? All right. At least for all the DVDs already issued. Okay? So in order to find the device key, they had to find the key somewhere in the clear in memory. Now, the software DVD player companies were doing everything possible to obscure that key, and they only needed it for a couple of milliseconds. Now, these guys tried everything, right? Slow down the program by hundreds or thousands of times, going to the debugger, because you have access to the binary. You can, right, disassemble it and do all kinds of things. It took quite a lot of effort. I mean, you didn't have thousands of people trying to do this, just a couple of lone people. But at some moment, one of the software companies makes a mistake, and in fact, releases a version that has debug information in it, plus an unencrypted key. That's all it took to find one device key. Now, you see, a device key, the system was designed from the beginning to resist breaching device keys, in the sense that if a device, they said, if a device key is breached, that would have been, by the way, very punishing for the DVD player manufacturer, because they said, we are going to revoke that device key, so no future DVD will have the key encrypted by that device key. Revocation is one crucial thing that you need to talk about in security. And then essentially that makes all the DVD players out there that have this device key bad. That would have been basically a riot on the side of the users, right? And so this is why they said, hey, make sure you protect your device keys. Okay? But it turns out that once they figure out the device key, they figure out how badly the whole scheme was put together, and within days they were able to actually derive the master keys and figure out how, I mean, the media key was encrypted with both a master key and device keys. And they figured out what the master key was. And that was a complete blunder on the side of the DVD designers. And in fact, within days, they breached the entire DVD system, right? So suddenly, you could decrypt any DVD without any problem, because once you have the master key, I mean, what are they going to do? Throw away all the DVD players, right? At that point, people said, yeah, let's focus on the next generation DVD players. Well, it turns out that that didn't go too well either, right? Because within a few days, they broke the the Blu-ray encryption, and all kinds of other things. So it doesn't seem to be on the side of the people that try to protect the media too much. I mean, that's maybe a good thing. But when it comes to the systems you presumably are going to design and use, right? I mean, there is no way to really resist a very focused, determined, massive attack on your system. What you want to do is resist the occasional user that, with very simple tools, might go and attack your system, right? So I mean, even when it comes to something like, for example, what Adobe did and so on, there are best practices that would have made the life much harder, but still to find some of the keys, it's very hard to protect all the 140 million keys, especially when people have very bad keys, right? So let's switch a little bit to that. And let's think about what's a better way to check that the password is correct, but at the same time, to make it very hard to derive what the password is by just having the information to check. So what we need is some sort of a one-way process. Okay, and this is one of the fundamental things in cryptography. Can you design so-called one-way functions? They're easy to apply in one direction and to check that certain things are true, but you cannot apply them in the reverse direction to determine who was the thing in the first place. Okay? But you see, brute force attacks are still possible on that, and you want to do other tricks to make sure that you prevent those. Right. So then a crucial notion is this one-way functions, and they can be used in many ways. Right? So I'm going to try to be more systematic on Thursday and to go through all of these slices, but I want you to have the big picture. Right? So one-way functions. Right? So these are functions, again, that can be applied in one direction, but they are very hard to reverse to figure out what happened in the other direction. Right? I'm actually sure I have some slides on MD5 of this. Let me see. Seems like, OK. So MD5 is one such function. So essentially what you want is this one-way functions are functions that scramble really well, right? So that the result looks very scrambled but deterministic. So it's crucial to understand that these one-way functions have to be deterministic. If they are not deterministic, you can't check that you have the correct input. So one way, for example, to check a password is you take the password. So what you do initially when you put the password first in the system, you take the password and you push it through this one-way function, and you get something called a hash. In order to check later that the password is correct, all you have to do is get a password prime, push it through the same one-way function, and compare the hashes. Okay? If the hash is the same, you have the same function. If the hash is not the same, you don't have the same function. The trick, though, is to design these functions so that it's impossible to revert them. If I have the hash, to compute the original password is hard. Right? So encryption, in principle, can be used for this if you keep a secret key, but then you have to hardwire the secret key in the software. The question is, could you design these one-way functions that don't depend on any secret key? They're just known not to be invertible. Right? Because if you do so, then you're not relying on some secret that could be divulged. Okay? So this is why this kind of hashes are one of the pillars of modern cryptographic systems. Right? Once I establish that you are who you are by having the right password, a simple comparison, if I push it through a one-way function, should suffice. Right? Now, it's not even clear if such functions exist, if things with the right properties can be put together. It turns out that all of that has been answered in the positive by the cryptography community. And trust me, you never, ever, ever want to design your own one-way function. And it turns out that they go obsolete. As our computational power increases, these functions become vulnerable to particular kind of attacks. So for example, MD5 looked great 10 years ago and is now useless. Okay? So MD5 is considered to be very weak. There are now modern replacements that are much, much, much better. Now, there is another particular trick you can actually do here. So this is still vulnerable to brute force attacks. It's vulnerable to brute force attacks with especially simple passwords, because all you can do is try various passwords. If you steal this, so imagine that this is stolen. And this is, you have to assume somebody is going to steal the hash version of the passwords at some point, because that essentially means just a direct attack on the computer system, and people are determined. They're going to stay there for months until they steal it, because usually they can sell it for a lot of money, by the way. Okay? And it's much safer than robbing banks. You don't have to go anywhere. You can just sit in pajamas and just type on a computer for sometimes months, but doable, right? So never ever assume I'm going to keep something away from people that want to attack the system. So in this case, you want to say, I'm going to lose at some point the hashes. Okay, somebody's going to steal the hashes and have knowledge of the hashes. The trick is going to be to make sure that even a direct attack in which you try passwords is not going to succeed, right, to find the hash. But if you just use a hash in a simple way, that's not possible. It doesn't matter how good the hash mechanism is and the fact that it's not invertible. You still have to check, for example, right, that the passwords are correct. And by checking that the passwords are correct, you have to apply the one-way function. So presumably, you could apply it for combinations of functions. Now, these are hash functions you better use. Again, no security through obscurity. You're using only hash functions that are, in fact, wildly used and wildly designed. So you have to assume that the attacker knows exactly which hash function you use. They have access to it. A brute force attack would mean just put in many variants of the password, apply the same one-way function, which can be done reasonably fast, is designed to be reasonably fast, and check against your hash. So one way to find the secret is to just try combinations and see which one unlocks the system. So an interesting question here is, could you strengthen such a system, even in the presence of relatively weak passwords, to make it much harder to break? Right? And the answer is yes if you use something called seeding. Right? What you're going to do is you add a random component to the key that the user has, and the combination, the user password and the random component, are pushed through the one-way function and then checked against the hash. Okay, I need to spend a little bit more time explaining how that actually happens. Right? First, let me give you this broader overview. So what I'm trying to say is, the cryptographic community has come up with best practices, very good mechanisms like the one-way hashes and how the seeding works and so on. The trouble is people don't use them, and they don't use them in the right way. So Adobe, right, these hash functions, MD5 was there for more than 10 years. SHA-1, which is a much, much better one, or SHA-256. Right, so you have SHA-1 or SHA-256. SHA-256 borrows from AES-256 mechanisms to produce the one-way function. I mean, it's really, really one-way. I mean, it's impossible. It's not known. I mean, even mild security exploits on it are not known, right? So these hashes, especially plus seeding, right, are considered to be strong. They are very hard to exploit, even with brute force attacks in which you just try 1, 2, 3, and whatnot, okay? But nevertheless, they were not used, for example, by Adobe. Adobe used a simple triple-dash encryption with some kind of a key that somehow they were keeping into the database engine to be able to actually decrypt, right? So when it comes to security, and I want you to understand this, it's not so much that you're not going to have breaches. You will have breaches. But ultimately, your job, your company, and how much you're sued and so on depend on how close are you to best practices. You see? Nobody can basically say, your system got breached, you get sued, because we all know that systems get breached. And nobody will successfully sue you if your system got breached. They will successfully sue you if they show negligence, as in, right? I mean, for Adobe, it's a disaster, because they say the standard, and there are open source tools that do this very well, the standard is SHA-1 or SHA-256 plus seeding. You use something that was dismissed 20 years ago by the security community. You have no defense against, oh, but I had the best system in place and I was just unlucky. It's not a matter of unluck, it's a matter of negligence. Okay, so this is what I want you to keep in mind when you go and design all of those things. All it takes is a little bit of Googling and find the right cryptographic libraries. Right? Even you do an open source project and you're putting together something in which people have to type passwords. Do yourself a favor, and even for that, and just go and Google and grab those widely available cryptographic libraries, right, that allow you to do the proper thing. It's actually surprising, but in fact, for example, PHP or almost any web design framework doesn't even allow you to do any more MD5, doesn't even allow you to do things in the bad way. So Adobe was really not using any of the modern tools, or they built in-house really lousy tools to get the major security breach, right? Virtually all the web front ends designed with open source frameworks are vastly more secure than what Adobe had in the back end, or vastly more secure than the PlayStation Network, in which they didn't even encrypt the passwords, right? So this is why resisting the temptation to design something in-house from scratch pays off big time. a lot of the frameworks, and this is really a great thing about middleware and frameworks, a lot of the frameworks are designed by people that understand better some of these issues. They are more concerned, they are more widely used, which means if an exploit is possible, it would have been discovered with higher probability. So this is why you're better off by, in fact, going and using an established framework, even if you work for a company that has lots of money and could design its own framework, right? Unless you really know what you're doing, you should never design your own cryptographic systems, because you start to look really bad, right? Like Adobe does, okay? So the building blocks when it comes to cryptography-related issues are symmetric keys, that's AES-256, asymmetric, RSA, and then the elliptic curves, and then hashes, these one-way functions, potentially with seeding, to make things less vulnerable. Good use of the security mechanism, putting them together, is essential, because the weakest link wins, right? Including things like writing passwords on a piece of paper. You lose the piece of paper, somebody knows that that's the password, that's bad. I mean, by the way, let me even make a recommendation, which was made to me by one of the people working at my company, Chris Dudley, right? So there is a fantastic program which is actually works on all the platforms and could be used to manage passwords. So what's the problem with passwords? The problem with passwords is if you can keep in mind one or two sophisticated passwords as a human being, or I mean really sophisticated passwords, but you never really want to type the password in an untrusted system. So what you can use, and this is a good technique, and that can be exploited even to design systems that have this property. You can use a sophisticated password locally to unlock something like a key ring and then extract a really sophisticated but automatically generated key to use on a website. So there is a program that does this, that makes your life easier. I mean, it's not hard to do, but it's annoying to do by hand. But a program doing this ends up being fantastic. Right, so this is KeyPass 2. This is open source, works on all the platforms, and has the same file format across all the platforms. So KeyPass 2 basically, it's a keyring manager. It has a little bit of an interface, allows you to do things, and has a very good generator for completely crazy passwords. Okay, so you go on you have a master password that's very complicated. You use that to unlock the little database that this KeyPass has. Your password is never typed into and never travels in any foreign system. You use it only on your local system. So any attack on that password has to basically happen on your machine. So somebody has to attack your machine, which becomes very expensive, has to be very focused. I mean, unless you have access to nuclear arsenal, nobody's going to really bother to attack your personal machine. The big problem is when you breach servers, right? With KeyPass, you unlock the key ring. What's a key ring? It's basically just a table, but it has to be kept secret. It's a table that says, for this website, I have this username, and this is the key. The application doesn't even show the key. It shows only stars. With double clicks, whatever, puts it in the clipboard and knows how to scrap it from there and whatnot. And then you go into the website, and you just, whatever, paste it from the clipboard. You won't even know what the password is, and it can generate these 20-plus key passwords that are massive that you never need to manage. All you need to remember is that one password that you never let anybody use. So the idea of key rings is very powerful and extremely useful, especially if the key ring is hosted on your own machine. Now, of course, you can, in the encrypted version, you can back it up on other websites. For example, since this is encrypted very strongly with AES-256 or some other thing that you can use, you can take the encrypted file and put it on, I don't know, a Box or these other services that actually host files now, right? Google Drive or SkyDrive or whatever, right? So one of the things that you could do in general is design schemes in which the actual password used to authenticate or unlock or do things never leaves the machine of the user that authenticates, okay? And of course, the question is, how can you still do something like this? And I'm going to describe a little bit of a scheme that could be used even when you have something like a server in order to provide such a service, okay? And the key is around, I mean, the main idea is around this asymmetry in the public-private key. It's not clear yet how to make such a monstrosity work, right? And by the way, one of the biggest results in mathematics in terms of beauty and how nice it is, and the highest impact result from mathematics was to explain how the RSA algorithm works and how you can obtain these symmetric keys. Okay? But if you have this symmetric key thing, right, then this is the way you can actually make things work. So this is going to be my laptop, let's say, and this is the server. Now, when it comes to cryptography, you have to make some assumptions that certain parts are strong. And the idea is to build on the strength of subparts to make sure that much bigger things are strong. Okay? What we are trying to do is accomplish authentication without even the need to store SHA-1 or SHA-256 keys on the server, and to some extent even without using a password in the normal sense of the word. Okay? Now, this will require somehow to establish that somebody is who they are by a certain mechanism, but once you do that, you can escalate everything from that. So the idea could be the following. And I still don't understand why people don't use things like this, because this is, in fact, the idea behind the automatic login using SSH. Okay? So this matches essentially what SSH does. So on the laptop, you're going to produce, there is, one second, there is some notation here which I might as well use it. Well, yeah, oops, that's my 5 minutes. Okay, so I'm going to use key for, no, let me write in words, okay? So I'm going to generate here, but it has to be generated in a cryptographically secure way, which means I need those cryptographic random number generators. I'm going to generate a public plus private key on my laptop, okay? I'm going to take the private key, and let's say I mix it up with a symmetric key locally just because I want to enhance the security plus key. But this never leaves the machine, it's only stored locally. Okay? Which means if you want to breach it, you have to breach into my laptop. Okay? Again, the big problem is when things are stored on the server and they breach the server and they get the stuff for 1 million people, or 140 million people like for Adobe. So the private key encrypted with a symmetric key, just because if you just got direct access to my laptop, I still want you to type a password, but this doesn't need to be super strong. It's going to be kept only locally. The public key is going to be placed on the server. So the only issue when it comes to authentication is once the public-private key pair is produced, to have some way to tell that this public key belongs to the person and who they are. And you can do that by all kinds of means. For example, if you design a system in which you have a hierarchy of super admins, and whatnot that need to give access, some admin at some point has to say, I verified by whatever means that this person is who they are. I've seen them or whatever. And I myself place their public key into the server. You can even do something called digital signatures, which I'm going to talk about Thursday. And the boss who put this guy's public key into the server can certify it in a way that cannot be forged, the fact that he put it there, which means auditing, he can be held responsible. Oh, why didn't you let this guy here? That means you didn't do your job at determining that he is who he is. Okay? Once the public key is in here, the way things work are the following. Okay? Remember, the private key cannot be derived from the public key. You breach the server, you get all the public keys, you still have nothing. This is how OpenSSL works. Okay? In order for the server to make sure that you are who you are, it does this. It generates a random number. It's cryptographically secure random number. It encodes it with a public key. It's called a challenge. And it sends it to you and says, I'm thinking about a number. What number is it? Unless you have the private key, you cannot guess that number. That number will have 100 digits or whatever. All right? So it's as easy as this. You can breach the server and it still doesn't mean anything. Okay? Now, you could, if you breach the server and can squeeze your own public key in there, you could get illicit access to the system. And you have to protect basically insertions into the database in some way. But you're never going to find out what my private key is from the public key, and it's based on the strength of the public-private key cryptography. And you need to use this only once to determine. So not only that this random number now allows you to certify that this is the right guy, but you can use it now as the encryption key for AES-256 and use it just for a couple of minutes, for example. And you can, again, every 2 or 3 minutes, you can put another challenge and say, let's change the keys. And then even if you somehow derived a partial key, and you breached it for the communication for 2 minutes, you switch the key, and then you're back to square one. So you only stole 2 minutes worth of communication between the servers, right? This is one of the strongest things you can do now based on the cryptographic protocols that we have, and is based on the pure strength of the public key cryptography, right? The private key never leaves the server. This is exactly how SSH works. You can derive this public-private key pair on your laptop. You take the public key, and by hand, you place it on the server, and then this kind of a protocol is used to authenticate you without typing a password. Okay? And it's considered to be significantly more secure even than any kind of one-way function. Now, this is not feasible if you have millions of users, because you have the problem of proving once that you are who you are. It's still left in the air, right? The proving that you are who you are is not built into the protocol. It just says, if you prove to me once you are who you are, once you have the pair, you already have an automatic mechanism that's very convenient. So that means you could do this, and this is what I'm planning to do with my own stuff. Make it hard to establish, to authenticate somebody. For example, you can use three-factor authentication, not password and things. So things like, I'll make sure you have control over an email address, over a phone, and maybe somebody knows you. And then make it very easy from that moment on. And make sure that this private key can be moved from laptop to laptop, for example, on a USB stick. And that will allow people to basically propagate rights. Okay, we're going to talk more about something like this Thursday. Okay, so I think there is a far cry from something like this from just use triple dash to encrypt some passwords like what Adobe did. Okay. All right, see you Thursday, and good luck with that project.